Today we're going to continue our discussion on how to graph rational functions. Yesterday we learned about the horizontal and vertical asymptotes, x and y intercepts, and how to sketch a graph. Before we begin our lesson today, I have somebody who would like to say hello to you. Go ahead.
Hi everybody, I'm Aubrey, Mrs. Dennis' daughter.
Alright, and she's up way past her bedtime, right?
Yeah.
Yeah. What are you doing right now?
Playing with Play-Doh?
Yeah, Play-Doh. Alright, go back and play with your Play-Doh. Okay, so I'm going to have you guys pause the video, and I want you to find all of the information in this table and go ahead and try and sketch the graph. Alright, we're going to find that the vertical asymptote occurs at x equals 0, and this is because the denominator cannot equal 0. When we graph our asymptotes, remember that we want to use a dotted line. Our horizontal asymptote will be at y equals 0. This is because the degree of the numerator is less than the degree of the denominator. When we go to find our intercepts, since the axes are both asymptotes, our graph cannot cross these axes. So neither one of them have intercepts. Another way we can figure this out is by trying to solve. When we try to find our y-intercept, we need to plug in 0 for x. So that would give us y equals 1 divided by 0, which is not allowed because we can't divide by 0. If I tried to solve for my x-intercept, I would do this when y is equal to 0, or when the numerator of my fraction is equal to 0. 1 equals 0 also does not give us something that can be solved. Now when we go to graph our values, we talked yesterday about picking x values on the left and on the right of our vertical asymptotes. Some people find it very helpful to make a t-chart. Since our vertical asymptote is at 0, we could plug in -2, -1, and then 1 and 2. Now remember, these asymptotes are kind of like magnetic fences that our graph is going to approach. If I plug -2 in, I will have 1/4. If I plug in -1, I will just have 1. +1, I have 1. Plug in +2, I get 1/4. Now if we go ahead and graph these points, our function, let's see if I can zoom in here. Oh, there we go. Alright, so at -2 we're at 1/4, at -1 we are at 1, and then at +1 we are also at 1, and at +2 we are at 1/4. Now it looks like my graph is slowly increasing. If I were to test this theory by plugging in other values, I could plug in, for example, 1/2. And if I plugged in 1/2, 1 divided by 1/2 squared gives me 1 divided by 1/4, which is actually 4. So at a half, my function will be up here at 4. And what I can see here is as my x and values on the left and on the right approach my asymptote, my graph is going to pull towards that graph, or pull towards that asymptote. And what we see is a graph like this. Now if we talk about common mistakes people make when they graph with their asymptotes, one mistake is that people want to make their graphs look like this. And that's not what we want. In that case, my function is not pulling towards the asymptote. We want the graph to pull towards the asymptote, so that is not what I want to see. Let's erase that. Alright, in terms of domain and range, domain is going to be all of our possible x values, range is going to be all of our possible y values. If we look at our graph, it continues to the left and to the right. The only value that is not allowed is 0. So for my domain, I could say from -infinity to 0, and then 0 to infinity. For my range, we can see looking at our graph that, first of all, we cannot cross the line y equals 0, and secondly, both sections of our graph are in the positive y region. So for that reason, we can say that our range is from 0 to infinity. Now notice on both of these that I have parentheses instead of brackets on my interval. Yep, there's that lightsaber again, remember that? Alright, parentheses, not brackets. Next we're going to talk about holes and discontinuities. When a function is not written in lowest terms, it is sometimes possible to cancel a factor. If you look at the example we have here in number 5, we can see that the numerator of this function can be factored. So if we were to go ahead and factor this, we would have x plus 3, x plus 1 over x plus 1. Well, what happens is that this common factor can be canceled. And when this occurs, there is what's called a point of discontinuity or a hole in the graph. And this occurs instead of the vertical asymptote. If we look at the resulting equation, this actually isn't even a rational function anymore. All that we have here is the equation f of x equals x plus 3. And if we think about it, this is a line. So visually, this is a line with a slope of 1 and a y-intercept at 3. However, we need to remember that there is still a hole in this graph. So this is actually a line with a hole. And the x value of -1 is still not allowed. So what you're going to do is you are going to plug in x equals -1 into the new reduced equation. So if we do that, if we plug in f of -1, we'll get -1 plus 3, which is 2. So what this tells me is that I am going to have, oopsies. What this tells me is that I am going to have a hole at -1, 2. So that'll be at -1, 2. So when I go to graph, I'm going to go on my grid and go to -1, 2, and I am literally going to put a hole there. And then I'm going to go ahead and draw the rest of my graph. I'm going to start at my y-intercept of 3, and then I'm going to do my slope of up 1 over 1. And what we'll see is that this graph looks just like what the function would look like, with the exception of there is a gap here. And another cool thing would be if you were to plug this into your graphing calculator and trace the function, you would see on the calculator, on the window where it gives you the x and y values, you would actually see that when it got to x equals -1, there would be nothing for the y value. And the reason why there would be nothing is because it does not exist. If you were to look into the table of values on the graphing calculator, and you were to look at the t-chart that it comes with, you would see, for example, -2, -1, 0, and so on. And we would see values all around it. However, for the -1, it would tell you error. Now, the only way that you will see the results that I've described over here on the graphing calculator is if you plug in the original function. So it's really important whenever you are testing your ideas and your graphs on the graphing calculator or in Desmos that you plug in the original function that we see here. Yep, that one right there. That function right there. That's the one that we want to plug in. On this next graph, you can see that our equations are starting to get more complicated. Now, if you were to plug this into your graphing calculator or Desmos to test theories, you would want to make sure that you put parentheses around the numerator and the denominator. The majority of this chapter will be without graphing calculator, but I want to keep on mentioning how you can check things in your calculator so that as you're doing your homework, you can still use that to make sure your ideas are correct. Alright, so first things first, when I want to find my vertical asymptote, I have to set my denominator equal to 0. So that'll give me x plus 2, x plus 3, and I know that when x equals -2 or -3, I am going to have vertical asymptotes. However, looking at this problem, it looks like it might be able to reduce. So I'm going to continue by factoring my numerator, and I get 3x times x plus 3. Now, once I have this factored, I can see that my problem was not in lowest terms. Since it wasn't in lowest terms, I am able to cancel off a factor. Remember, when you cancel a factor, what ends up happening is that you have a hole or a point of discontinuity instead of a vertical asymptote. So now what we can do is we can go down to this new section. We did not used to have an area for hole, and we can start by saying, okay, I know the x value is -3. And the way that I'm going to find the corresponding y value is by plugging -3 into my reduced function. So I'll go up here and I'll say, okay, 3 times -3 over negative 3 plus 2, negative 9 over negative 1, and my y value is at 9. So now I can go on my graph, and I know that I'm going to have that hole there. Now, since the other factor, the x plus 2, did not get canceled away, I still have a vertical asymptote at x equals negative 2. For my horizontal asymptote, what I want to look at is I want to look at the ratio of those coefficients. And what I can see here, if I look at my reduced function, whenever a function can be reduced, we always want to consider the reduced function from that point forward. So no longer are we going to consider the original unless we are going to the graphing calculator to test our theories. And let me just fix this. Okay, so looking at this, the ratio of the coefficients, I'm going to look at 3 to 1, means that my horizontal asymptote will occur at 3. For my y-intercept, I want to plug in 0 for x, so I will have 0 divided by 2, which is 0. And for my x-intercept, I want to set my numerator equal to 0, so 3x equals 0, x equals 0. Alright, so now that we have all of the pieces for our graph, we're going to sketch what we know and see if that gives us enough to draw in our function. First, let's put in our vertical asymptotes at x equals negative 2. Next, we'll put in our horizontal asymptotes at y equals 3. We'll put in the hole at negative 3, 9. And the x and y-intercept at 0, 0. Alright, now if we think about the things we've learned about our asymptotes so far, our asymptotes are guides for the graph. Our graph will never cross our vertical asymptote. And up until now, we don't think it can cross the horizontal asymptote. There are going to be some special cases, which we will look at in just a minute, but for right now, it does not cross either asymptote. So what we can do is this gives us enough that we can use that idea of the magnetic graph and just sketch in our curve using our asymptotes as a guide. If you wanted to pick additional x values around your vertical asymptote to make your branches even more accurate, you are welcome to do so, but you do not have to. Okay, the last concept that we are going to talk about today is how we can tell if a function crosses the horizontal asymptote. Now, I really want to stress that our graph will never, ever, ever cross a vertical asymptote. Vertical asymptotes, when crossed, would make our function undefined, so that will never happen. However, there are occasions where our graph crosses the horizontal asymptote. And to test this, we are going to set the function equal to the horizontal asymptote. Basically, what we are trying to see is, does this graph ever have a y value equal to the y value of our asymptote? So we set our function equal to the asymptote, and then we cross multiply to solve. If this equation is solvable and it has a solution, then the x value is the point where the graph crosses the horizontal asymptote. If, after you cross multiply, it results in an equation that is not solvable, then the function does not cross your horizontal asymptote. Okay, so to go ahead and take a look at this problem, we would first factor our denominator, x minus 3, x plus 3, or plus 2, giving us vertical asymptotes at x equals 3 and x equals negative 2. For my horizontal asymptote, since the degree of the numerator is less than the degree of the denominator, my horizontal asymptote occurs at y equals 0. For my y-intercept, I find this by plugging in x equals 0. So I have 0 over 0 minus 6, which just gives me 0. To find my x-intercept, we set the numerator equal to 0. So x equals 0, and again, we see that it is again the point 0, 0. As far as a hole, since nothing cancels, there is no hole. Not all graphs will have holes or points of discontinuity. Now to check where our function crosses the horizontal asymptote, we want to go ahead and set the function equal to the HA. For this problem, my HA occurs at 0. So I'm going to say 0 equals, and then the equation of the function, x divided by x squared minus x minus 6. From here I'm going to cross multiply. Now when my HA is at 0, that makes the problem rather easy, because when I cross multiply, 0 times the whole denominator gets knocked out. And the equation that I'm trying to solve is now just 0 equals x. And so what this tells me is that my graph does cross, and the point where it crosses has an x value of 0. Now when you're trying to find your y value, it's kind of obvious what it's going to be, because it's going to be the y value of your asymptote, which we'll see at 0, 0. Now many of you might have already figured out that our graph crossed our asymptote because we have intercepts at the same location as our asymptote, which is another dead giveaway that we have a crossing. Now when it's time to graph the function, we're going to plot our horizontal and vertical asymptotes and our intercepts the same way that we have done every other graph so far. Plot our vertical asymptotes, our horizontal asymptotes, and that intercept. Now the difference about this problem is now I have two vertical asymptotes and I don't have a whole lot of guidance. So I'm going to have to plug in some other values to see what my function is doing. You can do this by creating a simple t-chart, and with your t-chart you want to pick x values that are around your vertical asymptotes. So for example, I would pick -3, -1, I'd probably pick 1 or 2, and then I'd pick 4. And we do not need a ton of points, but we need enough to see how our function is behaving. So go ahead and fill out this t-chart and then try and plot an estimated graph for your function. Okay, as I plugged in my t-chart, I noticed that I'm getting a lot of decimals, and decimals are kind of a pain to graph. When we're graphing these are sketches, just like with the other functions that we were doing. The values that you're getting, the main purpose of them is to help you determine if the y value is above or below your asymptote. So with what I have right now, this negative value when x is at -3 tells me that my graph is doing one of these. And then if I look at this section in the middle between the -2 and the 3, I can see that when x is -1, my y value is positive. At 0, my y is 0. And then as x has values of 1 and 2, I can see that my y values are starting to decrease. And what this is going to look like is a squiggle in the middle. Alright, and then off over here, I see that when I plug in 4, I get a positive value of 2/3, and therefore I know that this piece of graph will be above the line. Since the only point where my graph is allowed to cross the horizontal asymptote is right there, okay, that's the only point where we're allowed to cross the asymptote, then I know over here and over here that that graph is stuck above the axis, okay? It is caged in there and it cannot go beyond. Alright, that's it for today. Hope you have a good one.